This is lesson 27, where we discuss measurement. And of course, measurements use lots of mathematics, and therefore it's important for us to know what measurements are and how to use them. First of all, what is the purpose of measurement? Well, the purpose of measurement is really standardization. We have standardized measures. And the rationale for this goes way back to when perhaps the distance measurement of foot was the length of the king's foot. And if you were lucky or unlucky enough to purchase something by length right prior to the death of the king, and the new king had either longer or shorter feet, what you bought and what you get would be two different things. And of course, we certainly couldn't standardize the king's foot by stretching or chopping off some of his toes. So eventually what had to happen is we had to come up with a measurement that was called a foot, and perhaps based on the length of a particular king's foot. But when that king left us, the amount of the foot stayed the same. And of course, the measurement system we use in the United States, which is really the English or sometimes called the standard measurement system, but most people call the American measurement system, is really quite difficult to use. Now you say, oh, no, it's easy. It's this metric system that's crazy. Well, the rest of the world uses the metric system, and after we discuss more about what measurements are and why they're important, we'll go into depth into the metric system. Now, in this country, the notion of standardized measurements really was seen after something called the Great Fire of Baltimore. And I believe it was back at the end of the 19th century. There was a huge fire in Baltimore. And fire engines came from all over the eastern seaboard, from New York, New Jersey, Maryland. And when they arrived at the site of the fire, they could not hook up, in many cases, their hoses to the hydrants. So even though they were there, they could not put water on the fire because the connections were not standardized. And probably many buildings burned down because of this. The decision was made to look into standardization. And of course, you know yourself that if you go to a car dealership in California, but you're from Florida, and you ask for a spark plug for your car, the spark plug they have there and the spark plug you'd buy in your native Florida would be identical. They're standardized. And there really is a very important use of standards. And of course, then if it's important, we need to have some governmental agency in charge. And we do have the Bureau of Standards, as well as states tend to have organizations within the state government that are concerned with standardized measurements. Now, why would you, as a consumer, care about standardized measurements? Well, the first thing is you go into a supermarket and you buy many, many things by their weight. Produce, meat and fish, as well as cold cuts, cheese. How do you know when the butcher, for example, puts a steak or some chicken on the scale and the weight turns out to be 2.5 pounds, that is indeed 2.5 pounds? Well, we must have standardized measurements, and someone actually comes and checks the scales. And if those scales are too far off, I believe in many locations, the store can be fined because we as consumers are assuming that the measurement of those scales are correct. It's the same thing when you purchase gasoline. Gasoline is purchased by the gallon. And again, a gallon of milk, you can actually see the milk in the usually clear plastic jug. But how do you see a gallon of gasoline? It's coming through the hose into your car. You never see it. You must trust that when the tank is full and it says 8 gallons, that indeed you have pumped 8 gallons through that gasoline pump into your car. Again, someone has to come by and ensure that a gallon on that gasoline pump is indeed a true gallon. Think about buying clothing. When you buy clothing and you buy, whether it's a particular size, a neck size or something like that, or when it's a small, medium, large, etc., you want to know that when you go to a store and you say, for example, I use a 17 neck shirt, I expect if I buy a 17 neck shirt with a 33-inch sleeve, which is the length of my sleeve, and I go home and try the shirt on, it will fit just right. It will fit the same as every other shirt I own of the same size. Could you imagine if you went into different stores or in different parts of the country and that same 17 neck, 33-inch sleeve shirt was different? I mean, you'd have to be trying on shirts or dresses or pants or whatever, hats, whatever you were buying all the time. And the fact is that we have standardized measurements, and typically a small or a medium or a large is pretty standard. And the fact is, without this, purchasing items that were sold by size would be incredibly difficult. So we do have standardization. And in fact, we even have standardization in terms of many of the restaurants that we visit. You visit a fast food restaurant or many other theme restaurants that are franchised throughout the country, and you know that when you're in a particular hamburger place or a particular Italian restaurant or pizza place, whether you're in Oregon or South Carolina or New Mexico or Vermont, you're going to get the exact same pizza, the exact same veal parmesan, the exact same cheeseburger, because the companies have standardized their measurements. For example, for the amount of cheese in a pizza, the amount of spaghetti sauce in the spaghetti, the amount of cheese that's placed on the hamburger, even the size of the hamburger and its bun. So one of the joys of traveling, if you call it a joy, is you can go into a familiar restaurant, get a familiar meal that looks and tastes exactly the same as back home, and you're 2,000 miles away. Some people don't think that's a joy. I'll leave that up to you. But without standardization, without standardized measures, we couldn't do that. And therefore, as we travel the rest of the world, we have a problem. Because the rest of the world uses something called the metric system. Now, the metric system, by the way, is the official system of the United States. It was adopted by Congress at the end of the 19th century. So it's been approximately 100 years, and we haven't learned. Yes, we do have 2-liter bottles, and we do participate, many of us, in 5 and 10K road races. And there are other measurements. We might give our young child 10 cc's of medication. But the fact is, we pride ourselves on being the only country in the world that uses this crazy system that's based on 12 of these and 16 of those and 4 of these and 2 of these. And it's nuts. So let's take a look at this metric system and to see why mathematically it makes a great deal of sense. The metric system is based around a series of prefixes. A prefix is a part of a word that comes at the beginning of the word. And here are some of the most important prefixes in the metric system. And here are those prefixes used with the meter. The meter is a measurement of length. And we'll talk shortly about how long a meter is. But right now we see we have a kilometer. Kilo means 1,000. Whatever the measurement is, if it's kilo, that measurement, it's 1,000 of those. Centi means 1/100th. Like a cent is 1/100th of a dollar, a centimeter is 1/100th of a meter. Milli, from 1,000, is a 1,000th of a meter. That is, a millimeter is 1,000th of a meter. What is a meter? A meter is a little bit more than a yard. Interesting enough, I was told a number of years ago a study was done, and this was a time when many people were very, very excited about changing over our entire measurement system to the metric system. And the question was asked, well, if we go over to the metric system and we change football fields to be, instead of each yard marker was 5 yards, 5 meters. That was using a meter. So the football field would be 100 meters long with 2 10-meter long end zones. It was determined that the vast majority of football fields, especially those in high schools and small colleges, could not contain a metric football field. So it's certainly very possible if we ever went to the metric system, we'd retain the use of the yard, if only for football. Because, of course, especially in the South where I live, football is a religion, and we certainly couldn't do away with our religion over a measurement system. Now, we would use a kilometer to measure very large distances. And we use a meter to measure moderate distances, and the centimeter and millimeter would be used for much smaller distances. For example, where is the meter used? Well, we see a 100-meter dash. 200-meter dash in the Olympics and in many track meets. We would use the meter to measure distances, for example, like the dimensions of a room would be in meters. The dimensions of a building would be in meters. Relatively moderate-sized distances, because remember, a meter is approximately a yard. So we wouldn't want to use a meter to measure the height of a human being, because most of us aren't more than we're less than 2 yards, and therefore be less than 2 meters. What we would use to measure greater distances would be the kilometer. I mentioned the 5K and 10K road race. That's the 5-kilometer and 10-kilometer road race. A kilometer, being 1,000 meters, is approximately about 6/10 of a mile. And again, there are many road signs throughout the country that indicate the distance not only in miles but also in kilometers. Obviously, in most other countries, the distances on road signs along highways would always be in kilometers. We have no problem understanding what a 10-kilometer race is, and therefore we should have no problem dealing with kilometers as opposed to miles. What would you use a centimeter for? Well, a centimeter, which is 1/100th of a meter, is approximately the width of a paper clip. A small, not a jumbo paper clip, but a small paper clip. And it's a fraction of an inch. And we'd use centimeters to measure, for example, the height of a person. Because certainly, if there are 100 centimeters in a meter, and a person, let's say, was approximately 1.5 meters tall, that would be 150 centimeters. You'll notice how easy it is to convert from meters to centimeters. Well, is it that easy to convert from yards to feet or to inches? I don't think so, because you got to multiply, let's see, a yard by 3 to get feet, and a foot by 12 inches to get inches. In the metric system, you look at the prefix and it tells you exactly what you're dealing with. How about millimeters? Millimeters are very small measurements. A millimeter is 1,000th of a meter. If you took that paper clip and opened it up so you look at the wire that actually makes the paper clip, the diameter of the wire is approximately 1 millimeter. In fact, I remember years ago there was a cigarette advertising campaign when they could advertise cigarettes on TV, and they talked about the cigarette being 1 silly millimeter longer. Really was quite insignificant in terms of length, because think about that diameter of that paperclip wire. But that was the campaign, and since most people had no idea what a millimeter was, obviously it stuck in people's minds. Whether they sold a lot of cigarettes, I don't know, because I didn't smoke then, nor do I now. But the fact is, millimeters have been creeping into our measuring system here in the United States. Okay, what other kinds of measurements are there? Well, there's measurements of mass. And here are the measurements of mass that are most common. We have the gram, the milligram, and the kilogram. These are, in fact, quite used in our system, and especially if you're shopping for many products. We'll talk about those specific products shortly. Now, notice I said mass. Really, the gram is a unit of mass, while the ounce or the pound are units of weight. What's the difference? Well, as long as we're on Earth, nothing. Your mass, you see, stays the same whether you're on Earth, in space, on the moon, on Mars, or on Jupiter. But your weight would vary quite a bit. In space, you are weightless. You have no weight, despite the fact that your mass hasn't changed. On the moon, you would have a weight much less than the weight on Earth because of the smaller amount of gravity. And in fact, if you recall, when the astronauts went to the moon, they jumped up and down like some silly children, and in fact, they could never have done that on Earth. But if you were on Jupiter and walking around, you would feel exceptionally sluggish, because the very large size of Jupiter contributes to a much greater gravitational force, which would enhance your weight to the point that you would barely be able to move, even though your mass has stayed the same. But we are not planning to go to Jupiter or to the moon in the near future, and on Earth, mass and weight really are the same thing. Well, let's see. The gram. What is a gram? The basic unit of mass in a metric system, a gram, is the weight of that paperclip, or the mass of that paperclip. So think about that. It's really quite light. And let's see, a kilogram. A kilogram is used in many cases in the purchase, especially in other countries other than the United States, of food. Meat, produce, the kind of things we buy by the ounce or the pound here, is sold by the kilogram. And an indication of how confusing this can be occurred a few years ago. Every summer I teach in an honors program in rural Nebraska. And one of the other instructors there is a gentleman from Iceland, where of course they're on the metric system. And one evening all the instructors went out to a restaurant, and the instructor from Iceland wanted to get a steak. He looked on the menu. There were 12-ounce steaks, 10-ounce steaks, 8-ounce steaks, 16, even 20-ounce steaks. Of course, this is Nebraska, where they raise cattle. And he was confused. What is this 10-ounce steak? And no one else at the table besides myself could explain to him what a 10 or 12 or 16-ounce steak was in terms of kilograms, because they didn't know. I was the only math teacher there, and therefore I was able to quickly indicate to him the precise, or fairly close precise size in terms of kilograms of the individual size steaks. And he purchased the steak because he knew exactly, once I told him the weight in kilograms, he knew exactly what he wanted. Milligrams are quite useful. We use milligrams all the time. If you pick up a package of food and you look at the label about the nutrition in that food, you'll see milligrams of sodium, milligrams of cholesterol, grams of fat. All this is on the label, and those of us who are concerned about excess cholesterol or excess sodium are very concerned about looking at milligrams. A milligram is 1/1000th of a gram. Now think about that. Consider the paperclip. That paperclip was a gram. If we took that paperclip and cut it into 1,000 equal pieces, each of those 1,000 pieces would weigh or have a mass of 1 milligram. Not very much, but again, when you're looking at that label and you see 25 milligrams of cholesterol, that really isn't a lot in terms of the actual amount of cholesterol, but in terms of your intake of cholesterol, might be quite concerned and might not buy that product. Okay, a kilogram, by the way, is approximately 2.2 pounds. So if, for example, you go over to Europe and you want to buy some oranges, and you buy 5 kilograms of oranges, that would be 11 pounds. And I hope you would truly enjoy your oranges, because they'd probably rot before you ate them all, unless you had a very large group of people with you. Okay, what else do we measure? We measure capacity. We have quarts and gallons and pints. And I'm sure most of you have memorized how many pints are in a gallon or how many ounces in a quart, etc. Probably not. Again, the metric system is exceptionally easy. We start with the basic unit of liter, and a liter is approximately a quart. We all know what a 2-liter bottle of soda pop looks like. Well, it's just 2 liters. And of course, we have milliliters, which would be 1,000th of a liter, that we'd use for very small amounts. Okay? And therefore, I would think, based on our purchase of 2-liter bottles, our purchase of, or actually not more than a purchase, but actually giving dosages of medicine that involves milliliters, I think most of us are quite familiar with those words, those measurements, and should have no problem adapting to those if indeed we throw out the gallons and the quarts. I mean, obviously you might want to buy a 4-liter bottle of milk if you normally get a gallon of milk. It would be very similar. In fact, that reminds me of a story. Years ago, back in the late 70s, we had was called the gasoline crisis here, the oil crisis. And in many cases, to get gasoline, you had to get gasoline on odd or even days. If your license plate ended in an odd number, you could get on odd days, the 1st, the 3rd, the 17th of the month. And I was visiting family in Florida and went out to get gas for the car because it was the appropriate day to do that, and got on a long line in this road leading up to the gas station. And at that time, the price of gas was about $1 a gallon. And as I was getting closer and closer to the gas pumps, it looked as if the price was about 25 cents a gallon. And I couldn't believe this. I mean, here was a point of time when the gas prices had risen up high. Gas was really restrained in the amount that was available. People were lining up to get it, restricted on when you could get it. And yet here was gas that was about 1/4 the typical price. Until I got closer. The price of gas was 25.9 cents per liter, which was much more than $1, not much more, but somewhat more than $1 per gallon. So it was very interesting, and I have not seen gasoline sold by the liter in this country since then, and it's been almost 20 years. So, but again, it was not that difficult to deal with capacity measurements in liters and milliliters. Okay. How about area? We talked about area earlier, and we said that the basic unit of area is a square whatever. Well, for example, a square centimeter. That would be a square that each of its sides was 1 centimeter, and the area would be 1 square centimeter, so that we would use that to measure area. How many squares of 1 centimeter on a side could we fit on the surface? For example, if I wanted to measure the area of a table, we'd measure that in square centimeters. If I wanted to measure the area of a yard, let's say to buy fertilizer to fertilize my grass lawn, I would probably use square meters. On the other hand, if I was measuring the area, the land mass area of a town or a county, I would use square kilometers. Certainly wouldn't want to measure square kilometers in my room on the floor, nor would I want to use square centimeters to measure the land area of a town or a county or a state. How about volume? Now, volume is really different than capacity. Capacity generally measures liquids. Volume is measured in cubic measurements, cubic inches, cubic feet, also cubic centimeters. A cubic centimeter is simply a cube, all of whose sides are 1 centimeter long. We use cubic centimeters in many cases, because you see a cubic centimeter is exactly the same as a milliliter. Isn't that interesting? Is a cubic inch the same as an ounce? I don't think so. But a cubic centimeter is exactly the same as a milliliter. And the cubic centimeter of water, by the way, has a mass of 1 gram. So capacity, volume, and mass are all connected very nicely in the metric system. It's not true in our system. How about measures of temperature? In a previous lesson, we discussed Celsius and Fahrenheit temperatures. Here are 2 thermometers with the boiling point and freezing point of water lined up. Basically, what happened, I am told, again, in one of those other circumstances where I wasn't there, that Fahrenheit, when he built his thermometer, believed that the freezing point of water was approximately 32 degrees above the absolute coldest temperature. How wrong he was. He made the boiling point of water 212 degrees to separate from 32 by 180 degrees. The reason he used 180 degrees is 180 is divisible by so many numbers: 2, 3, 4, 5, 6, 9, 10, 12, 15, and 20. So it was easy to make gradations on its thermometer for other temperatures between the boiling and freezing points of water. The metric system said, hey, look, we just as soon use a system based on 10 and 100. So basically the freezing point of water was set at 0, and the boiling point of water was set at 100. And we know we can get a lot colder than 0 degrees Fahrenheit, and it can get a lot colder than 0 degrees Celsius. And as mentioned in the earlier discussion of this, if you're over in a country, most of the other countries in the world that use Celsius temperatures, and you woke up and the temperature was 30 degrees, that would be a very pleasant day. And the reason is because 30 degrees would be quite equivalent to a temperature of Fahrenheit that you would find most comfortable on a summer afternoon. And we talked, again, if you skipped over that, the conversion of Celsius and Fahrenheit back and forth, we talked about in the lesson on the graphing in the coordinate plane. But again, once you get familiar with the Celsius temperatures, it's no big thing. Quite frankly, if I said to you the temperature outside was 50 degrees, and I asked you to step outside to see if I was telling the truth or not, you might not be able to tell unless it was exceptionally hot or exceptionally cold. If the temperature was 60 degrees or 45 degrees, I don't think you'd be sensitive enough to recognize that it was not 50 degrees. So we think we're familiar with measurements, and we're really not. There are some special units of measurement. The first one I want to discuss is a light year. A light year is not a measurement of time, despite the fact that it has the word year in it. A light year is a measurement of distance. It is the distance that light travels in 1 year. It is obviously a very long distance because we take the speed of light, which is approximately 186,000 miles per second, multiply it by 60 for the number of seconds in a minute, multiply it by 60 for the number of minutes in an hour, multiply it by 24 for the number of hours in a day, multiply it by 365 for the number of days in most years, and we get a number that has 6 and a whole lot of zeros after it. 12 zeros. That is 6 trillion miles. That's how far light travels in a year. And we use the light year to measure distances in space. In fact, if we wanted to go someplace that was 1 light year away, and we were traveling at 186,000 miles per hour. Now think about it, 186,000 miles per hour is faster probably than any vehicle we have, rocket plane or whatever it might be. But if we could travel that fast, 186,000 miles per hour, it would take us 3,600 years to get to that location 1 light year away. Now, since most of us don't plan to live that long, we would have to send astronauts out and have them have families in space, have their children have children, and many, many, many generations, and more than 3.5 millennia later, they would land on this planet. Obviously, before we can travel that far in space, one of two things has to happen. We have to be able to go faster than 186,000 miles per hour, or we've got to be able to put ourselves in suspended animation. But that's another story. That's for our science classes. But basically, the light year is a distance measurement. And one must understand when they talk about how many light years something is away. By the way, the sun is 8 light minutes from Earth. We were told that it takes about 8 minutes for light to travel from the sun to Earth. And therefore, that distance is 8 light minutes. Another measurement is the acre. We talked about area earlier on. We mentioned the acre. It's one of the few measurements of area that does not have the word square in it. And an acre is approximately, or actually equal to, 43,500 square feet and is used to measure land. So the next time you see a sign that says 2-acre lot for sale, you'll know that that's 87,000 square feet of land. A hectare is the metric measurement equivalent to the acre. It's used for measuring land. A hectare is equal to 10,000 square meters. In case you're interested and you want to convert, 1 hectare is 2.471 acres. Basically, if you live in a house and you have a half-acre piece of land and you have to mow the lawn, then you have an understanding what a half-acre is. But most of us, acres and hectares are kind of irrelevant unless you're in the land business. The last thing I'd like to discuss is rates. And we talk about miles per hour. If we go 200 miles in 4 hours, we're going 50 miles per hour. If we're going 280 miles and we use 14 gallons of gasoline, we use 20 miles, we got 20 miles per the gallon. The word per means divide, out of. If we scored 237 points in 10 games, we scored 23.7 points per game. If we listen, if you plug our radio in, any place in the United States, the electricity is at 60 cycles per second. And if we listen to a station that's located 96.7 FM, that's 96.7 megahertz. A hertz being a cycle, mega being million, so 96,700,000 times a second, the little electrons in your radio go back and forth. So we've looked at measurement. we've looked at measurements and realized why measurements need to be standardized. We looked at measurements of length, of capacity, of weight or mass, of volume, of temperature, of area. We've looked at some very special measurements, and now we've concluded this lesson and talk about next in lesson 28, problem-solving techniques.